In the previous video series, I showed you how you can use an STM32 based platform to do digital signal processing for audio applications. In the first video, we looked at a brief introduction to the hardware and looked at some basic low and high pass filters and how we can implement those in software, and then showed a real-time demo. In subsequent videos, we looked at notch filters and then also looking at the tremolo effect, which is some form of amplitude modulation. It was briefly shown in the first video, but I'd like to go into far greater depth in this video of how to do the basic and low-level software or firmware setup. That includes STM32 Cube IDE, double buffering, initializing and writing a small driver for the codec, doing DMA stuff with the ADC, and so on, just so you know how the basic firmware is set up and you can transfer this to whatever codec or whatever platform you are using. If you've seen the previous videos, you know I'm using the STM32 F405 RGT6 to be specific, which is a pretty powerful ARM Cortex M4 based STM32 microcontroller. So it has its own dedicated floating point unit, quite a sizable amount of flash and RAM, and quite a lot of nice peripherals, and it also does I2S, which is basically SPI, which is used to communicate serial digital audio data between the processor and the codec. The codec that I'm using is a pretty inexpensive, low-power stereo audio codec. There's nothing special about it. It has 2 channels of input, various output channels including a headphone driver, and it has an I2S digital interface. So we'll be using this datasheet along with STM32 Cube IDE to write the basic firmware required to get data in and out of this codec. Here again, just a brief overview of the hardware platform. This board was produced and manufactured by JLCPCB in China. You can see it's fairly small. Here's a Eurocoin just in comparison. We have the main STM32 F405 microcontroller, various interfaces including USB, serial debug and so on, power supplies, the main codec, and some analog conditioning for the input and output side of things. And here you can see I've very crudely mounted this board in a guitar pedal enclosure, which lets me control settings via potentiometers, input and output jacks for the guitar and amplifier, and an on-off switch. Just for clarification, here is the block diagram of this platform. Again, processor and codec communicate primarily via I2S to relay ADC and DAC data, but we can configure this codec via I2C, which is something we have to do to set up sample rates, bit depths, and so on. I have different power supplies, again, some various connectivity over here, analog front ends, and then my audio input and output. Thank you to JLCPCB for sponsoring this video. As I just said, the boards were manufactured and assembled by them. If you'd like to get your own boards produced, I have a very similar audio codec with a slightly more powerful STM32H7. If you navigate to my GitHub repository at github.com/PMS67, and then navigate to the DSP audio system on module. In this repository, you'll find all the hardware design and manufacturing files ready for assembly and manufacturing at JLCPCB. Also, a huge thank you to Altium for sponsoring this video. If you'd like to try out Altium Designer for yourself, they have a free trial, and you can get 30% off your license purchase if you choose to do so. You can go to altium.com/YT/Phil's Lab. On my channel, you can also find a variety of videos on Altium Designer, how to use Altium Designer, including a very long 3-hour video going from starting a project to actually getting your boards ordered and manufactured. As usual, I will be using STM32 Cube IDE to do my development of the firmware and software. This is a free IDE provided by ST and lets you program all of their STM32 devices. So I'd recommend, if you want to follow along, just go to the site and click Get Software to download it. It's completely free. Once you are in STM32 Cube IDE, you need to go to the top left, click on File, New, and STM32 Project. Once this is loaded, you can type in your part number of the chip you're using. And again, I can go to KiCad just to look at my schematic, and this is my MCU. I'm using the STM32 F405 RGT6, so that's wanted to transfer over to STM32 Cube IDE. So once you've typed that in, you can find the part number here. You can see what package it is, the flash and RAM, how many I/O, and so forth. So click on that, click Next, and give it a project name. I've just called it GDSP base firmware, and then we can just click Finish. I'll be writing this code in C, but of course you can write this in C++ if you wish. So once the project has been created, you'll be greeted with this view where you define the pinout of your device. So you can either do that by clicking on certain pins and then choosing what they should be, or you can go on the left here, expand these menu items, and then for example select SPI, UART, and whatever you need. The way we're going to do that is essentially take the pinout from the schematic and then just transfer that over. Most notably, we need to enable serial debug because that'll be our main programming interface with this programming connector over here. We need to enable our crystal and select that this is a 16 MHz crystal. And I'd like to enable, for example, USB, but predominantly we want to enable the I2C lines, which is I2T2 on these pins over here, and I2S with a master clock. So let me just transfer that in STM32 Cube IDE. So for example, I2C2 I want, so I can click on here, and then enable this like so. And you can see it's already chosen the right pins, PB10 and PB11. Remember to always verify with your schematic. So let me just do the pinout for the rest of this as we just saw, so very simply, and then we'll go into more detail of how to set up things like DMA and so forth. So here I've selected my main peripherals. Of course, this isn't everything, but this is a good basis for us to get it started. I've enabled I2C to configure the codec, I've enabled I2S, which is under multimedia, and I've also enabled the master clock output, as this is something the codec requires. I've enabled USB, and you can also go down to middleware and click on USB device to enable, first of all, the communication device class. This enables a virtual COM port so I can stream or send various data back and to the host and device. I've also enabled the crystal over here. We still need to go to the clock configuration, but before that we also have this LED pin enabled here. But this now just says GPIO output, so you can right click and enter user label and also type in LED. And LED is always good to enable if you have it on your board, just to, as a first basic check to make sure the firmware uploads and you can run this and flash an LED. I also have my serial wire debug enabled with a trace output. So let's go to the clock configuration by clicking over here. Click no to start with, because you want to change the input frequency to our high-speed external crystal, and remember from the schematic that was 16 megahertz. So I typed in 16, I'm selecting my PLL source to be a high-speed external, and I want my target frequency to be the maximum possible, which is 168 megahertz. Click enter, and then it'll ask you if you want to find a solution using different sources. Just click OK, give it a bit of time, and there we go. It's changed all these prescalers, all of these PLL values, to make sure that for our input frequency and our desired main clock frequency, all of these other frequencies and values are correct, given all of these constraints. Now we can move on to actually going deeper into this basic setup that includes setting up DMA streams and so forth. Because we just want to do very basic setup with our I2C connected to our codec, I won't be using DMA for that. Initially, our codec will just be set up at the start before we go into our main while loop, before we do our main callbacks, so we don't really need to use it that much, especially not for very high bandwidth transfers. So for I2C, we can just leave everything as it is. What we mainly need to change is our I2S settings, because we want that to have a certain bit depth, want that to have a certain sampling frequency, and so forth. So we can go to multimedia, click on I2S2, and then we can go to parameter settings first of all. So here you can say we have different transition modes, and we want it to be a master transmit. The communication standard depends on your codec, but most common for these audio codecs is I2S, the Philips protocol. Now this next part is depending on your application, what bit depth you want and so forth. The easiest to set up is of course just 16 bits data on a 16-bit frame. If you want a higher resolution, you can of course go to 24 bits on a 32-bit frame. But let's just stay with 16 bits data and 16 bits frame. And that's what I've been using in the previous videos as well. Now our audio frequency, I believe the codec supports everything up to about 96 kilohertz, but because we want to give ourselves more time when we process our samples, we want to select a lower sampling frequency. So I will just be going with 48 kilohertz for now. So the next part is the real audio frequency and the error between selected and real. Now we want to have 48 kilohertz exactly ideally, but because of our clock configuration on this page and the various PLL settings, in particular this PLL I2S setting over here, we will actually get a different real audio frequency. Now what you can do is go to the clock configuration and play around with these divider values and so on to get it more close to whatever your selected audio frequency is. In this way you can decrease the error between selected and real. For me and for our purposes, this is close enough. But remember, when you're doing any digital audio processing or signal processing, you need to take into account the actual real audio frequency or the sampling rate, not this 48 kilohertz. The rest you can leave the same with the I2S PLL clock and the clock polarity being low. This is our main basic setup. However, we want to use DMA. DMA essentially offloads the CPU of this microcontroller. That means essentially all these data transfers can happen in the background via this discrete memory access controller. So we go to DMA settings, and we need to add two streams essentially. One is to transmit, so one we want to send audio data to the DAC, and one we want to receive when data has been sampled by the ADC. So click on add, and first of all let's set the transmit stream. You can see it's actually called SPI2_TX because I2S is pretty much just a fancy SPI. It's basically the same thing, more or less. It automatically chooses the stream for us, and the direction is memory to peripheral because you want to send data. Priority for these kind of things I set as high or very high, and the mode should be circular. For example, if you want to transmit a stream of bytes, if we do normal, the transmission will stop after that and won't repeat every time we fill up a buffer. We'll have a buffer that we continue to fill up with data after we've processed it, so we want the DMA stream to constantly transmit that data, and that's why we use the circular buffer. This you can keep the same, however we want our data width to be not a byte, because that's just 8 bits, you want it to be 16 bits, so half a word, and that's both for peripheral and memory. And that's all there is to it. Now, for 24 bits, of course, you would have to go higher, but that's why 16 bits is so easy, because we can just select half word. Now, basically, we want to do the same thing for our receive stream, so we go add I2S2 X. And X is our receive stream, essentially, and this is peripheral to memory, and again, priority very high. We want this mode to be circular for the reasons described before, and our data width, because we want 16 bits, to be half word for both. And that's pretty much all we need. We can go to system call and then go to the interrupt controller over here, and you can see all of the relevant interrupt flags have already been ticked for us. So this is pretty easy. What we can do is then click on this save icon here, and this can then compile our code. Keep in mind, however, that the schematic actually shows us that I2S2, the receive and transmit data streams are actually on PB14, PB15, because this made routing a lot easier. So I can either control click, and you can see PB14 is now highlighted in blue, and I can move that over there, and same for PB15. There we go. This means all of my I2S pins are nicely grouped. It wouldn't make sense to do the routing like so, especially if I have all of these free pins. After saving, STM32 Cube IDE will have generated quite a lot of code for you. This includes the USB drivers, we have the I2C and I2S initializers, DMA stream initializers, and so on. So this is a pretty good canvas to start writing our very low-level code. Now remember, HAL isn't entirely optimal, and you can optimize many things, and also the way we will be writing this low-level firmware isn't maybe the most optimal way, but it gets a result very, very quickly, and is a good starting point for many of these applications. Before we can continue, we should look at double buffering, because this is something you should always do if you're doing graphics or audio processing. It essentially gives us more time to do the actual processing while the DMA controller loads data into our buffers. The way we do that is essentially have an ADC buffer and a DAC buffer, and we essentially split those in half, so to speak. So while the DMA, for example, is loading in half of our buffer, we can process the other half of this buffer as shown via this EE times figure over here. So we do this both for the output data as well as the input data. It's also called a ping pong buffer because you always ping and pong between these two halves of the buffer. So while we're gathering data or while we're transmitting data of half a buffer, we are processing the other half of that buffer. So keep that in mind with the steps we're going to be doing next. I'll leave some links in the description, for example, to this EE Times article on double buffering to help you understand that a bit better. To start, I would then like to create two signed int16 type buffers, one for the ADC data and one for the DAC data. Remember, we're using int16 type because we wanted a 16-bit signed integer conversion from our ADCs and DACs. The first thing I do is in my define section, define a buffer size. So you can play around with this depending on what kind of latencies you can tolerate in your system. So a larger buffer will give us, of course, more time for processing, but it will introduce a larger delay into the system. Once we have those, we can create two buffers, one for the ADC and one for the DAC. So here I've created the type int16t, an ADC data buffer of buffer size, which we can define over here, and the same thing for the DAC data. And this is what the DMA streams will access. Now these buffers aren't really enough for double buffering. We want to essentially point to the location we can process while the DMA is filling the other half. So we need some sort of pointers to keep track, okay, which part of the buffer can we write to and read to. And here we have these buffer pointers. One is the in buffer pointer, one is the out buffer pointer. And initially, the out buffer pointer just points to the beginning of our DAC data buffer. This way, the ADC data and DAC data buffers are used by the DMA, and for our processing, we will just be using these buffer pointers to let us know, okay, we can access these sections of these buffers while the DMA is loading the other half. But we'll get to that with certain callbacks. So nicely for us, the hardware abstraction layer, or HAL, provides two callbacks for the I2S DMA streams. One is a transmission reception complete callback, so the DMA stream will transmit and receive at the same time for the ADC and DAC data, and we also have a halfway complete callback. This is really useful for us and for double buffering, because once the transmission and reception has reached halfway, we can then change our pointers, and once we've reached full way with the transmission and reception, we can flip our pointers again. I will also create a processing ready flag to indicate when a transfer is complete via the DMA stream to let our system know, okay, we can start processing audio data now. And I'll do that via means of a flag, which can then be checked, and then we can call a function. And I've simply called it the data ready flag, which will set to 0 in our int main. When data ready flag is set to 1, we can check that and say, okay, now we need to process data. As I just said, the HAL gives us two callbacks via the DMA streams. One is when the transmission and reception is halfway complete, so we've gone through half the buffer size, and another callback for when the transmission and reception is completely complete. In the first halfway callback, we essentially set our pointers to say, okay, we can process the front part of the ADC data and store that in the front part of the DAC data. This is because the DMA has essentially sent and filled the front part and now is working on the last part of these buffers. So this is really convenient. Then of course we set the data ready flag equal to 1. Our buffers will then point to half of the buffer length which we can process. We do something very similar for the completely complete callback, so to speak. We set our input buffer pointer and output buffer pointers to the final half of our buffer, because now we've completely completed our reception and transmission of that data, and the DMA stream will now continue with the first half of the buffer again. Then again, we set the data ready flag. And so all the time we are ping-ponging between these two halves of these buffers. So in this way, while the DMA is loading or transmitting data, we can process the other half of the data and store it in the other half of the buffer. So this is really a very useful concept, and this is something you should always use for audio and pretty much graphics processing as well, I believe. Now we won't fill this function in yet, but I'll just do a processing data function, which then, after processing and after looping through these buffers, will set the data ready flag to 0. So here I've written the process data function, or rather the skeleton of it. Essentially this process data function then gets called whenever the data ready flag is 1 and that's been checked in the main while loop. Let's go through it step by step. We need to know that the codec actually works in stereo, so our ADC buffer and DAC buffer actually gets filled with left data, right data, left data, right data, and so on. I've created, just for simplicity, static floats that give us the left input sample, the current left output sample, and the same thing for the right channel. What we then do is loop through half of the buffer length using this loop, always in increments of 2, because remember, for every point we're at in the buffer, we have a left sample, and then plus 1 of that, we have the right sample. So we loop through half of the buffer is important because we're doing our double buffering, where we only look at half of the buffer at one time. So for the left channel, we get the ADC input, we convert our int16t type to a float using this conversion factor here. That's pretty much just dividing by 32768 because we have a 16-bit int. I'll do some sort of shifting here just to make sure the values are in range between +1 and -1. And then here is where actually the processing happens, and we assign our output sample, which is some function of the left input sample. Then before sending it back to the DAC, we need to convert our output sample from a float back to an int16, and that's essentially just multiplying by 32768. Then casting it to an int16, and then filling that into wherever our output buffer pointer is pointing to, and remember that was happening in these callbacks over here. Exact same thing happens for the right sample, and that's it. At the end, after we've looped through, we can then simply set our data ready flag to 0 and wait for it to be set to 1 again before we redo our processing. So in here is then essentially where the magic would happen. We would process our left input sample and process our right input sample with some distortion, reverb, delay, or whatever effect you're currently working on. So that's pretty much the core of it. Of course, we still have to initialize our codec, but we'll do that after this. The last step is that we actually have to start these I2S DMA streams. And the way we do that is in int main after all of this configuration. So somewhere here, before we go into our main while loop, we need to start our DMA streams. So I've already written the function out for us here. And in Cube-IDE, if you control click, you can go through to that function prototype, or the function definition rather. And you can see all of the parameters and so on. So let's go through that one by one. This function starts the transmit and receive DMA streams both at the same time, which is really useful because we don't want to start the ADC stream and the DAC stream separately. We can do it all in one. We need to pass it the I2S handle we're using, which in our case is I2S2. We need to pass it a pointer to whatever buffer we want to transmit, and a pointer to the buffer wherever the DMA stream will put its data it's received into, and then of course the buffer size. So very, very easy function, and it does everything for us. It returns a HAL status type def, so we can check basically is the return of this function HAL okay, and then that means, okay, looks like everything, at least with the transmit and receive streams, has been set up correctly and might be working. So I've transferred that over here. I'm just calling this function our I2S2 handle, the DAC data as our transmit data, and our ADC data as our receive data with the whole buffer size. And then I can store my status as a HAL status type def variable and then check if that's HAL okay before I continue on to our main while loop. So of course any other initializations and checking that this is all working should be done here. And of course before we call this, we need to initialize our codec, and we'll do that in just a second. The last thing we need to do then of course in our main while loop is check if the data ready flag is equal to 1, and if that is, we need to call our process data function. And of course, any other thing you do, for example, flashing the LED, you would do in here as well, for example. Okay, with that done, we just need to then initialize the codec using I2C and the datasheet. For the TLV320 codec, which we saw at the beginning of the video and the datasheet as well, I've already written a very, very crude driver that essentially just sets certain register values to enable us to set the proper sample rate, bit depth, and enable the inputs and outputs of this device. And this is something you have to go through quite carefully in the datasheet. The datasheet will contain sort of these application informations, and for us, quite importantly, also these register maps on page 48. And these you have to go through depending on which codec you use, kind of one by one, and these will tell you what functions you can access when you write or read from registers. One, for example, might be the software reset, which I would recommend you do every time you start this device. Both to do a hard reset, there's an actual reset pin on this device, as well as software reset. And then we need to set, for example, the codec sample rates. And this is quite involved, some of these calculations, depending on what sampling frequency you want, what master clock frequency you want. You have to choose all of these PLL values for the Q and J values and so on. So quite involved. And this depends, for example, if you're using 96 kilohertz or 48 kilohertz. And all of this is detailed in the actual datasheet. It shows us how to choose all of these PLL values for the Q, PR, KJ, and so forth. So quite involved and maybe just a bit too long for this video. I'd like to give you a general overview what needs to be done, at least as a minimum, to get this device to run. This will depend very heavily on your codec, and that's why I won't go into too much detail. What I haven't shown you in the beginning, that I also enabled the reset pin, which is inverted logic for this codec, which I can just toggle before I start writing by I2C to this device. So essentially I'll just perform a hard reset, and then I'll start writing to these registers. So we'll go through them one by one, but I have several of these codec write register commands, and if I scroll down, you can see I've written some function prototypes which essentially simplify this HAL I2C register write function. If you'd like to know more in detail of how to write a very simple I2C driver, I have a video on my channel called How to Write a Driver. But essentially I have write register and read register functions, as well as this codec reset function, which essentially just toggles this end reset pin on the codec. So every time you see this write register function, all I'm doing is calling this write register HAL I2C function. First thing I do is perform a software reset after a hard reset. Then I set all of my PLL values to make sure for a given M clock frequency I'm getting 48 kilohertz out. The same thing you have to do for the DAC as well as the ADC, so these are the two register settings over here. Then I have to unmute the left channel. In this case I'm just using mono, so I'm muting the right channel. I'm routing the line 2 to the left ADC, selecting certain amplification values and so on. I'm powering up the left ADC and the left DAC. I'm setting a common mode voltage. I'm unmuting the left DAC channel. I'm routing the left DAC to the left line output, unmuting the left line output, and finally setting some sort of clock value. This is just to show you there's actually quite a bit of register writing required before you can actually get any data in or out of this device. A lot of it is fairly silly, so to speak. That means powering up or unmuting channels, but it's something that can maybe bother you a bit if you don't know what's going on and why you're not getting any audio out or in. So really make sure you read the register map and read the entirety of these audio codec datasheets. So with that driver in place and with the header included, I can simply call this codec initialize function, passing my codec struct, my I2C2 handle, which GPIO port I'm using for the end reset pin, and this will then call this function which writes to all of these registers. Then I do a short delay, as we saw before, starting my transmit and receive DMA streams. And then basically my processing should begin automatically after this DMA stream is initialized, using these callbacks and then calling this process data from the main while loop. So that's pretty much all there is to setting up the low-level firmware. But remember, you really have to go into detail into this codec datasheet. One last thing I'd like to add and talk about is the fact that we have these GPIO or ADC inputs which are routed directly to the ADC channels of this STM32 F4 microcontroller. And the previous videos I've been using these ADC channels to read, for example, switches or potentiometer values to change control settings of various effects on the fly. For example, the filter bandwidth or the volume of my guitar effects pedal. So I'd like to show you how I can get a fixed sampling rate on these ADCs and also read this data in via DMA. Schematically, you can see I have about 8 ADC channels going in, and we might only be using a couple of them, but I'll show you how to read in, for example, a number of these ADC channels using DMA at a fixed sampling rate. So here I actually have the firmware version open, which I use in the videos, and this has a few more things configured than what we've just seen, but it's very much built upon the principles we just looked at. You can see I've enabled all of these ADC channels here, from channel 0 through to 4. You can either do that by clicking and then just selecting which ADC channel you want, or you can go into the analog section over here, click on ADC 1, and then tick the boxes for which ADC channels you want. Then we need to select the ADC settings. Remember, we don't want to just have this sample at some arbitrary rate. We want to have a fairly slow rate, let's say maybe 10 or 100 Hertz, because this will be user controlled. The user won't be changing this the whole time, and we don't need a very high sampling rate. For the ADC settings, I'm using 12 bits, so anywhere from 0 to 4095 I will be able to get out. I want data alignment to be right alignment, and this is pretty much always the case, and I want scan conversion mode. Scan conversion mode, I'm reading essentially more than one ADC channel at one time. I'm leaving this continuous and discontinuous conversion modes untouched because I will be using DMA continuous requests, meaning the DMA can continue request measurements from the ADC, so I need to enable that. The number of conversions is 5 because I've set up 5 channels in this case, and I have various ranks, so depending on what channels I want to sample first, I will put that as rank 1, and then the less significant channels at rank 2, 3, 4, 5, and so forth. In our case, it doesn't really matter which order we sample them in, so I've just done it by 0, 1, 2, 3, 4, 5. Sampling time, I typically go something fairly high, so how many cycles per sample it'll take, so how many clock cycles. 3 cycles far too short, so something for fairly decent accuracy and giving us enough time to sample, I would say about 144 cycles. We don't need to sample very fast, remember, for this. One thing I've just jumped over, which we need to come to now, is the external trigger conversion source. And I've set this to be a timer 2 trigger out event. And this is because we want to use a timer that then actually triggers these ADC readings at a fixed rate, so 100 Hz, kilohertz, or whatever you require. So I've selected timer 2 trigger out event, and trigger detection on the rising edge is pretty much standard. So given that, we then need to set up the timer, of course, for a certain sampling rate. So we go to timers. So we want to go to timer 2, set the clock source as internal clock, and we'll just set channel 1 to be PWM generation with no output. We don't want to actually route this to any pin. This is essentially just to trigger the ADC readings. Down here, I've selected the trigger event, which is normally on reset. We want that to be update event, and this is so that the ADC can be triggered by this. You also see I have these prescaler and counter periods over here. And combine this prescaler and counter period lets us essentially downsample the input clock frequency, which is used to control this timer 2. Now, if we go to the datasheet of the STM32 F405, we can find timer 2 over here. And this is connected to the APB1 bus. Going back to our clock configuration STM32 CubeIDE, we can see our APB1 bus is over here with the peripheral clocks and the timer clocks. So the timer clocks are at 84 MHz, and basically we do 84 divided by 33,600 divided by 500 is our sampling frequency. You can see this -1 in both cases because the actual conversion adds +1 to both of these values. So I've indicated it rather directly that I'm subtracting -1. So if I do the calculation, which is 84 MHz divided by my prescaler, which was 33,600 divided by 500, you can see I get actually sampling frequency or sampling rate of 5 times per second or 5 Hz, rather slow. This is how you can use the prescaler and counter period to change the sampling frequency of these ADCs, and then remember the trigger event selection to be update event, and then the ADC selection, of course, use the timer 2 trigger out event. So every 1/5 of a second or every 5 times per second, all of these 5 channel conversions will be launched by timer 2. However, we don't just want to sample at the correct time, we also want to load our data that we receive from our ADCs via the DMA into memory. The way we can do that, as usual, is go to DMA settings and add a stream, which I've already done here. You can see if the mode is circular, that means after a conversion, the DMA just doesn't stop doing requests, it continuously does requests. So in circular mode, and because we're using 12 bits, we need to be able to store that properly, so I use a half-word data width. And remember, our DMA setting, continuous requests, was enabled in the ADC settings over here as well. So that's all you need. You can click Save. Now we've enabled our DMA request for the ADC and are triggering using the timer 2 update event. Then in our code, what we can do is add one more buffer, essentially, for our ADC control data. So our ADC control data is different to our audio ADC data. It has a size of 5 because we are reading 5 values, 12 bits, so we need to use an unsigned int 16 type to hold these. Then in main.c, after we've initialized our codec, after we started our I2C transfers, we need to start our ADC DMA stream using the handle for ADC1. We need to pass our buffer in. We want to read 5 ADC channels. After that, we can start our conversion timer, so to speak, which is timer 2, using the HAL TIM base start function. And that's pretty much it. So I hope you enjoyed this video on how to do the low-level basic firmware setup for this guitar effect pedal, which we've been using in the previous few videos. Looking back at video 1, I actually showed you what the basic software overview is, and I hope this video has cleared this up. We initialized the codec via I2C, we set up our I2S DMA audio streams with all of these complete and half-complete callbacks, including setting flags. We started our ADC control readings and saw how we can use a timer to trigger ADC readings, for example, to update the effect parameters. And then, of course, the rest is data processing in our process data function. So thank you very much for watching this video. If you liked the video, please leave a like. And if you haven't already, please do subscribe to my channel. There's much more electronics, DSP, and control system videos to come. I look forward to seeing you there. Bye-bye.